Okay.
Okay. Yeah. You can start. So let me just briefly introduce you. So Dominic Jansing, he's a senior research scientist at Amazon Research. And then he's going to talk about non-statistical notions of independency causal discovery.
Okay, so I mean, you have probably heard how conditional independences are employed for causal discovery. But the idea of this talk is to show that statistical dependencies are just one kind of dependencies that are employed for causal inference. And although the ideas I'm presenting, quite some of them are not at a stage where they are heavily used in practice, but it's more a direction for the future that I'm trying to show. Of course, with the goal of inspiring young researchers. Non-statistical notions of independence in causal discovery. Oh, why do I see two slides at the same time? Is this usual? Yeah, okay. Okay, so what does statistics tell us about causality? So you might have seen Reichenbach's principle of common cause, telling us that if two variables x and y are statistically dependent, then either x causes y causes x, or there's a third common cause of both. And of course, the cases can occur simultaneously, which makes the problem even more heavy to distinguish between those cases. But what is also important that Reichenbach already postulated that in case 2, there should be conditional independence, so x, y independence z, given z, if z is the common cause. So the idea of what causality is supposed to show has been nicely shown by Pearl, nicely phrased by Pearl in his functional model of causality, where he assumes that every node xj is a function of its parents and an unobserved noise term. And he assumes that all noise terms are statistically independent because otherwise one wouldn't call it noise in this setting. And then it's important that these functions that describe every node as a function of its parents and the noise have a causal semantics in the sense that the functions describe how xj changes when the parents are set to specific values. So it's not just a relation between observations, it also tells us something about the direction of the cause. If we assume this model of causality, then one can show that there are four equivalent notions of the causal Markov condition. It's basically the existence of such a functional causal model. Second, the local Markov condition, stating that every node is conditionally independent of its non-descendants given its parents. The global Markov condition that describes all independences via deseparation, because the local Markov condition implies further conditional independences that are not explicitly stated here. Then what is also important for this talk is that the causal Markov condition implies that the joint distribution factorizes into the conditional distribution of every node given its parents. And so this is the mathematical condition, but these conditional distributions have a certain philosophical meaning, in the sense that every such conditional describes a causal mechanism. So the idea is, although there may be different factorizations of the joint distribution that don't necessarily respect the causal ordering, this factorization, which respects the causal ordering, is not just mathematics, because the terms here correspond to different mechanisms. But the main idea of this talk is that causal inference in real life is not only done on the basis of statistical dependencies. Also, the similarities of single objects require a causal information. So if you just see these two chocolates, then you observe that they are similar, and the natural explanation is that they come from the same factory. And on the other hand, not all similarities require an explanation, because if you observe that those two t-shirts have the same stripes, then you wouldn't necessarily infer that one company copied from the other one, because this pattern is so obvious that it doesn't require a common cause as explanation. So these two different cases are supposed to show that similarities only require an information if they are sufficiently complex. But how do we formalize complexities? And a very nice construction from the fundamental point of view is Kolmogorov complexity. So Koimogorov complexity of a binary string just measures the length of the shortest program that outputs a certain string on a Turing machine. And the interpretation is it's the number of bits required to describe the rule that generates this string. There's some, okay, no, I should skip that. That's too much detail here. So strings with low Kolmogorov complexity cannot have much in common. Some problem with Kolmogorov complexity is that it's uncomputable in principle, so there can't be an algorithm that computes it. But it's nevertheless a very interesting construction for theoretical purposes, because it provides a probability-free definition of information content, so just for single objects. There's also the notion of conditional Kolmogorov complexity. K of y given x is the length of the shortest program that generates y from x, from the input x. So it's the number of bits required for describing y if x is given. So the idea is that it describes the length of the shortest program that, no, sorry. In contrast to K of y given x, there is a slight modification, K of y given x star. It's the length of the shortest program that generates y from the shortest compression of x. And this is a subtle difference because X can be generated from its shortest compression, but not vice versa, because there's no algorithmic way to find the shortest compression. So if you have the shortest compression, it's more information than having the string itself. What is very helpful about Kolmogorov complexity is that it allows for a definition of mutual information that is in strong analogy to Shannon mutual information. So if you have two strings, then the information of X about Y and vice versa is the information content of X plus the information content of Y minus the information content of both. So this is the number of bits saved when compressing XY jointly rather than compressing them independently. And this is supposed to visualize this. So if you have the star and the dot and just the star, then the information that those two images have in common is just the star. So that would be the algorithmic mutual information. There's a very strong analogy to statistics. So if you replace the strings, which are supposed to formalize the objects, with random variables x, y, and replace Kolmogorov complexity with Shannon entropy, and you replace algorithmic mutual information with statistical mutual information, then you have the same equations that you have for Shannon information, also for Kolmogorov information. And we want to stress this analogy even further and postulate an analogy of Reichenbach's principle of common cause, stating that whenever two strings x, y are algorithmically dependent, then either x caused y or y caused x, or there is a common cause causing both, which means that every algorithmic dependence in nature also requires a causal information. And the distinction between these three cases also uses conditional independences in analogy to the statistical case. So we have the complete analogy to the statistical case in the same way as every statistical dependence requires a causal information. Also, every algorithmic dependence requires a causal information. So if you observe that, for instance, two images allow for a more efficient joint compression as opposed to independent compressions, then these two images are related, so they have a common source in a sense. But in the statistical case, we know that causal discovery requires conditional independences. And in the same way, we also need conditional mutual information to do causal discovery on single objects. So conditional mutual information of x on y given z is the information of x given z plus information of y given z minus the information of xy given z. So it's the information that x and y have in common when z is already given. And again, we have a formal analogy to statistical mutual information. So Shannon mutual information between X and Y given Z would be entropy of X given Z plus entropy of Y given Z minus the joint entropy of XY given Z. And accordingly, we would define conditional independence. Whenever the mutual information between X and Y given Z is close to 0, we would say X and Y are conditionally independent given Z.
Hi, Dominic. Sorry
yeah.
to interrupt. I'm sorry I couldn't introduce you. So we have a question from the audience that I think is relevant to make.
Okay. I didn't see that.
Yeah. So so someone is asking that in the example of the strings that you were mentioning, then if the strings are algorithmically independent only if the mutual information is 0, if that's the case.
Yeah.
Yeah, okay. So we have another question. Let's say William is asking, suppose that I observe eyes in two species, A and B. They are similar in structure and function. Under this argument, they are causally related? So that's the question.
I missed the beginning of the question.
So it says, suppose that I observe eyes in two species, A and B. And the eyes are similar in structure and function. If under this argument, they mean that they are causally related. So the eyes in the two different species that have the same structure and function.
Okay, yes, they are causally related by the common history of evolution, I would say.
Yeah, so and we have a third question from Adam that is related to the previous one. And he's saying, what is the causal interpretation of the star and then the star with the red circle in it? I think this relates to one of the slides that you had before when you were showing the
causal. Okay, so the fact that I have to put a star here for the definition of independence. No, sorry.
Yeah, I think this refers to the previous slide.
I mean, that slide.
Yeah.
On the right.
Yeah, exactly.
The causal relation.
The question is, what is the causal interpretation of the star and then the star in the red with the red circle in it? So I think it's a clarification of what this expression means.
Okay. So let's say you have a file that that encodes these images. Then you could ask, what would a very good compression algorithm observe? Then a good compression algorithm that is able to recognize this similarity would compress it more efficiently because it can describe the star once instead of describing it twice.
Thank you, Dominic. I think we don't have any further question.
Okay, thanks for the questions. I appreciate that. Okay, so now having seen this strong analogy, we just postulated that the causal Markov condition can also be phrased for conditional algorithmic independences. So if you have n observations formalized as strings and G describes their causal relations, then every xj is conditionally algorithmically independent of its non-descendants given its parents. Okay, so why would we postulate that? That's the question I will address later, but first, what is nice from the math point of view that the equivalence of the different Markov conditions can also be shown for algorithmic independences. So for n strings, the following conditions are equivalent: the local Markov condition, the global Markov condition that deseparation implies conditional independences, and a recursion formula for joint complexity. So like the Kolmogorov complexity of all the strings together is equal to the sum of the conditional complexities of every node given its parents. So this replaces the factorization of the joint probability. So it occurs quite common that logarithm of probabilities are closely related to Kolmogorov complexity. So for that reason, the factorization turns into a sum rule. So we have another analogy to statistical causal inference, but I mean, we have just postulated this Markov condition. So regardless of all these nice mathematical analogies, we should ask whether it's justified that to postulate that. And to support that, we tried to copy Pearl's justification of the statistical Markov condition by a functional model and formulated something that can be seen as an algorithmic analog of Pearl's functional causal model. So let's say you have n causally related strings, x1 to xn, and every xj is computed from its parents and an unobserved string via a Turing machine T. So you assume that at each node there is a Turing machine that gets the information from the parents and an unobserved noise strings. And you observe that all these noise strings are algorithmic independent. Then you can say that these noise strings describe the causal mechanism, so the program that generates xj from its causes. And again, this uj is the analog of the noise term in the statistical functional model. If you assume this model, you can show that that the strings satisfy the three equivalent algorithmic Markov conditions. So in a way, we have justified the algorithmic Markov conditions if we assume that in nature, every causal mechanism can be simulated by a Turing machine. It's in a way, it's the Church-Turing principle applied to each node. So whatever mechanism you have in real life, it should be able to simulate that via a Turing machine. That's the idea. Then we can do some causal inference for objects, which I just showed schematically. So let's say you have three carpets and you look at the pattern, then there is some figures, some symbols that appear in A and in C and in B and in C, but all the common figures that symbols that appear in A and B come from C. So A and B don't share anything that is not already in C. So this is also a notion of conditional independence. A independent B given C. There is a question. Should I?
So there is a question. So the question is, this is interesting, but how can this model complexity be extended in the continuous case? We are assuming that we can express objects with strings, but if we start to think about uncountable spaces, I think that this assumption is quite difficult.
If we have continuous spaces, yeah.
Yes. So if we start to think about uncountable spaces, I think that
Yeah.
A question from Federico.
Well, it's a good question. I think usually I would answer by discretization. I mean, in practice, there is only a finite accuracy anyway. And if you choose discretization fine enough, then it's beyond what you can resolve anyway. So I think this would be a workaround, although it may not feel nice from the conceptual point of view. So there is no, maybe there should be a continuous notion of Kolmogorov complexity, but on the other hand, as a counter argument, I mean, if you think of quantum theory, then you have discreteness when after you resolve nature fine enough, you may have discreteness anyway. So it's hard to say whether this is really a caveat or whether we can accept that.
Thanks, Dominic. I think we don't have any further questions.
Okay. Okay. So as I said, Kolmogorov complexity is uncomputable. So it's very nice for some proofs, but in practice we need computable information measures. And the question is, oh, there's two questions. Come here. There's
yeah, so we have two more questions. The first one from Reese. So is the compression you are talking about related to inducing the latent variables in objects? For example, clothes can be described by several latent variables. One of them would be the branding, for example, the Nike tick. If you can introduce the latent variables, is that enough? So that's a question from Reese.
Yeah, that's a nice question. In fact, I already thought about that, to what extent representations like variational autoencoders should also be considered some kind of, so maybe that's the modern way of compressing information. I think that in fact, one should rewrite these ideas in a way that is more adapted to deep learning. So that's a very nice idea, and I'm happy to talk about that with people who really understand deep learning. So it's not my field. And so I was more working in the traditional computer science, theoretical computer science setting.
Nice. Thanks for the answer. We have another one from Chris.
Yeah.
I said, but a variational autoencoder compresses to a fixed point based on the structure of the network. So, but it really depends on how you encode the encoder and the decoder that you use, and the neural network that you have there, and how that's going to be fixed in the structure.
Sorry, that was a bit too much for me. Well, what was the question exactly?
So the question is, Chris is saying that a variational autoencoder compresses to a fixed point based on the structure of the network, so that you have a bottleneck there. So he's saying
so the question is whether the fixed point would somehow respect
exactly
the network. I'm not sure whether I understand it entirely because of my limited knowledge of these things. So it's the question whether a good representation of variation autoencoders in variation autoencoders would provide a generating model that is close to the true generating model.
And I guess the limitation that you have because of the fixed structure of the neural network that you have in the various.
So I tried to unmute Chris, but he says that he doesn't have a mic.
Okay.
Microphone. So maybe what we could do is on the discussion session, maybe this is another point we can talk, we can revisit. Yeah.
Yeah, I can see that there's lots of questions this direction. Let me maybe, since there are so many questions, I would like to answer the questions, but and I can skip quite some material in this slides instead. So I'm maybe it's better to answer to the questions now if this is fine.
I think Chris is trying to grab a different computer so he can mute himself and we can have a discussion about this.
Okay.
But so I don't think we have any other questions. I think everything we have.
Okay. So
we can move ahead.
The question is if we look at empirical compression algorithms, although they don't really provide Kolmogorov complexity, we can ask whether they define an interesting information measure in its own right. So there's no rule why Koimogorov complexity should be the only way to measure non-statistical information. So every compression algorithm in a way defines by compression length some information content. But the question is, if it does, could we also postulate a causal Markov condition with respect to that information measure? And first of all, the question is whether every information measure defines a reasonable notion of conditional independence. And it turned out that whenever an information measure satisfies some conditions, for instance, a monotonicity, which is pretty obvious. So if you add something, you cannot have less information. But there's also an important condition called submodularity. I cannot go to the details there. It's well known in optimization. It's a quite common assumption on set functions. Then you can show that maybe I skipped an important part here. Then you can define conditional mutual information in strong analogy to Shannon information as well. So whenever your information function satisfies submodularity, you can define conditional and mutual information as, so the information of S, T given U, as information of S and U, T and U minus the information of S, T and U, and minus the information of U. You can figure out that this is exactly how you can generate, how you can compute Shannon conditional mutual information from Shannon entropies. Was there an additional question? Or?
So this was Chris mentioning that he has a microphone already. So maybe we can go ahead and we can leave.
Yeah. Okay, so one can show that also every submodular information measures allows the definition of a Markov condition on a DAG with the equivalence of 3 different formulations of the Markov condition in analogy to what we had before. I don't want to go to the details there. So we can, in principle, define a Markov condition for every submodular information measure. But the question is, for which information measures does that make sense? And if we recall how we justified the Markov condition in the algorithmic sense and how Pearl justified the Markov condition in the statistical scenario, we just try to copy that. And maybe I should skip that. I tried to copy the definition of a functional causal model for the scenario of a general information measure. So the statement that the noise objects are independent just reads that the information of all n objects are the same as the sum of the information of all the separate descriptions. The fact that the causal mechanism is deterministic is rephrased by the statement that the information of the node, its parents, and the noise is the same as the information of the parents and the noise. So it just means that the effect only contains information that is already contained in its observed or unobserved causes. So all the information is already there. And then one can show that the existence of an R-functional model implies the causal Markov condition with respect to R independence. So maybe I should talk a bit about the interpretation of that statement. It basically says that whenever you have, you're considering a class of causal mechanisms that admit a functional causal model with respect to your particular measure of information, then it is justified to postulate a causal Markov condition with respect to that information measure. And just to show you some examples, let's say you define a functional model of plagiarism. So let's say there is a text T1 and another author copies part of the text or just takes many sentences from the text or many words and generates his own text. Then let's say if you just measure information in terms of bag of words, then we would assume that the author adds some of his or her vocabulary and takes some of the vocabulary of the first text. So that would be a functional causal model of plagiarism. A slightly more sophisticated one is a functional model where you copy also substrings from a text and merge them to new strings. And one can show that this functional causal model fits to Lempel-Ziff compression algorithms, in the sense that whenever you measure conditional dependence via Lempel-Ziff compression length, then and you have causal mechanisms that are given by this kind of string insertion and string deletion, then you can postulate a causal Markov condition with respect to Lempel-Ziff compression length. Because one can show that Lempel-Ziff compression length is basically submodular with up to some small error term. Okay, I would like to skip some more material because I would rather like to have more time for the questions, because that would be a bit fast. If it's okay with you guys.
Yeah, we can do that. Maybe we can unmute Chris so we can have the discussion that we started before. Mauricio, can we do that?
Chris, you should be able to talk now.
Hello, Chris.
Can you hear me?
Are you there?
Yeah.
Can you hear me? Can you hear me?
Yes.
Oh, okay.
Yes.
That's all right. I cannot hear myself, so therefore I don't know. Obviously I can hear myself, but not coming back through the speaker, so I don't know if you guys can hear me. But no, what I was just saying, and I think I just piped that into the Q&A chat window as well, is that both Kolmogorov and Shannon depend on non-lossy compression to achieve anything meaningful, because that's how you measure the data or the information content in the data, and that kind of then flows into the descendants where we're looking at KL divergence or anything else between two data sets or mutual information criteria. A variational autoencoder is a different beast because its compression ratio crucially depends on the neural network structure, and therefore the compression that's achieved there is potentially lossy. Which means you're no longer really measuring the data, you're measuring the structure of the tool, if you know what I'm trying to say. So I don't see how that could be brought to bear in this particular use case, because we were doing very different things. Does that make sense? That was my only misgiving here with the mentioning of variational autoencoders, or its brethren really, in the neural network community. They're very good at compressing, yes, but they're doing it in such a way that you probably cannot use it in a meaningful way to get at information criteria and similar metrics.
Yeah, that's a good comment. However, I think that depending on the use case, you may be interested only in certain aspects of the objects. And in case the lossy compression captures those relevant aspects, the idea may still work. But I mean, okay, of course, this is very fuzzy, and this would be an entire research project, maybe even a research project for years. So for that reason, let's say I wouldn't abandon the idea for that reason.
Okay, fair comment. But thanks for that.
Okay, thank you, Chris. Thank you, Dominic.
Yeah, I don't think we have any further question in the chat. So Dominic, I don't know, maybe you want to wrap up. We're almost at time.
Yeah. So okay, that's nice. So maybe also to wrap up, just one comment on what I skipped. So what I skipped is also some part that we currently work on which is quite sophisticated. And the idea is that even if we have statistics, it may also be important to look at non-statistical information in the statistics. And just to give you a flavor of what this means, is that if you decompose the joint distribution into the conditionals of every node given its parents, in the usual causal Bayesian network scenario that you probably have been talking about this morning, then we add another postulate stating that we have an algorithmic independence of conditionals. So the algorithmic independence of conditionals states that those conditional distributions here correspond to independent objects of nature, and therefore they are algorithmically independent, in the sense that the shortest description of the joint distribution is given by separate descriptions of the conditional distributions given the parents. And this is a condition that, that adds an algorithmic aspect to the statistical level. I don't want to go to the details there for lack of time, but just wanted to say that we try to explore that also for confounder detection, this independence of mechanism postulate. So, and the wrap up is just that looking at non-statistical measures of information adds a valuable level to the usual statistical perspective.
Thank you very much, Dominic, for the amazing talk. I don't think we have any further questions, but if people want to think about the talk and think about any further question, we can maybe discuss them later after we in the roundtable. So thanks again.
Yeah, thanks for the invitation.
Thanks to you. It's been great. So now we have some time for lunch, and we'll be back for the afternoon talk.
Okay. So.